Hi, I'm Laura Rahala, and on behalf of my co-authors Herschel Ellis, Chase Casher, Jamal Longwood, Nabel Tay, former students they are, and my colleague Richard Rahala, we're all from Kennesaw State University, and our presentation is Lunar Cargo Transportation, LuCaT, Semi-Autonomous Vehicle with Suspended Cable and Solar Power. Today we're going to go through an introduction, design synthesis, vehicle dynamics, power requirements, thermal control, and then I'll wrap up with a summary. So we're going to start off with the introduction. What are the motivation? What were we trying to do? Where? Why? What's the goal? How are we going to do it? What's our idea? We're also going to talk about the requirements and the initial design assumptions. Let's get started. The ambitions for further space exploration have grown in recent times. So we're proposing a transportation system to transport cargo on the lunar surface, specifically on the southern pole of the moon near the Shackleton crater. Reasons for that location: there's long-term sunlight, and also there's evidence of water ice. So we're trying to come up with a system to transport, among other things, water ice. Water ice is important on the surface of the moon, not only for drinking water, but for oxygen, hydrogen, rocket fuel, cooling, radiation shielding. The goal is to create a system to transport items faster and more efficiently than the lunar rover. And we're going to utilize cable suspension system with a fully contained vehicle that's semi-autonomous. The idea is to take a suspension vehicle, add together lunar capabilities, and make it as fast as possible. You can see various requirements here. I'm going to highlight that the maximum velocity, we'd like it greater than 8 miles an hour, with a payload mass of about 750 kilograms. And of course, it has to be disassembled and reassembled on site. We'd like to have solar charging, and we're looking at a steel cable. The lunar environment, it has this abrasive lunar regolith dust. If you look at the very famous photograph on the bottom left, that's a footprint of an astronaut on the moon, and it really highlights the lunar regolith dust. But if you look at the photograph on the right side, you can also see this dust. This dust tends to be sticky, and so you can see it all over the astronaut. Also on the moon, we have a gravity that's about a sixth that of Earth. There's no aerodynamic drag, extreme temperatures, and lack of convective heat transfer. Speaking of these temperatures, it goes from real cold to real hot. We would like a capacity to carry up to 750 kilograms of cargo. We're targeting a total mass full load and vehicle of 1,500 kilograms, and it'd be great to go at about 8 meters per second, which is 18 miles an hour. Design synthesis. Here's a video of the LuCaT. Okay, so looking at the top isometric view, you can see on top we have a solar panel, and then the nacelle is a shield where we hold the drivetrain, etc. It's riding on cables, and then there's an arm to which we have a container attached, and that's where we would put the cargo. You can see the chassis frame with the drivetrain. You can see the wheels, the motor controller, batteries, etc. The left shows a top isometric view with the solar and the optical solar reflector panels removed. You can see the protective housing, and then the bottom isometric view also shows the OSR panel on the lower surface. Material selection. So we've got extreme temperatures. So we selected aluminum using an Ashby analysis, aluminum 775 T6 for the protective housing. Since the strengths of this material at cryogenic temperatures are high, but admittedly the strength is lower at higher temperatures. But we're hoping insulation can help alleviate the high thermal loads. Here are some of the specifications of the LuCaT. Now let's talk about vehicle dynamics. The axles are supported by ball bearings, and friction calculations performed using equations related to wheel ball bearings. We added an additional 5% of vehicle weight for additional frictional losses for unknown reasons. The transportation route is broken into 3 sections that go between 4 different stations. The first section's between station 0 and 1. The second section, which is much longer, is between sections 1 and 2, and then sections 2 and 3 is smaller. The main transportation route would be between stations 1 and 2. And we assumed 100 seconds to reach cruising velocity with a constant acceleration between 0 and 8 meters per second. In the paper, you can read all about our dynamic analyses. I'll just illustrate. There's lots of equations in there, of course. And then the dynamic results. Now we're going to talk about power requirements. Okay, so we needed to determine the power required and the number of batteries required. We used a rectilinear approach, assuming a system's a point mass. You can read all about it in the paper. Based upon calculations near the lunar South Pole, with constant solar radiation assumed in a direction that's incident horizontal, meaning it's coming in directly from the side due to it being on the south pole of the moon. Frictional effects were the focus of the losses, and we decided on a cylindrical solar array. And then there's solar panel parameters. Okay, so we looked at the energy required for 80 kilometers, both with and without solar, and clearly the solar was going to benefit this a lot. The number of batteries with solar was found to be about 9. But looking at the power requirement for accelerating and cruising at the 8 meters per second, we could see that we actually required closer to 12 batteries. So 8 meters per second was determined to be the optimal speed. The power at 8 meters per second required 12 batteries. And the power requirement was more than the energy that then was required for the 80-kilometer trip, and so we went with the 12 batteries. After a complete one-way trip of 80 kilometers, the LuCaT would need time to fully recharge its batteries using its solar panels before the return trip. You can see how the batteries would be stored. Thermal control. So there's no cooling via convection due to the thin lunar atmosphere. So conduction was used to transfer waste heat from the batteries using a solid heat sink. Heat losses were calculated using the internal resistance and current applied to the batteries to determine the waste heat that would need to be rejected by an optical solar reflector, OSR, in conjunction with a solid conductor heat sink. To prevent overheating of electronic components through the protective cover, insulation was sized. And again, we used aluminum 775 T6 for the protective housing. So we optimized the surface area of the optical solar reflector, the OSR. And we also found that the number of layers of insulation that were required was 30. Here you can see the housing parameters. The OSR rejected waste heat generated by the batteries, and 30 layers of insulating shield allowed only 3% of solar radiation to be transferred into the housing. Summary. So we met the goals. Greater than 8 miles an hour. It's actually closer to 18 miles an hour, or 8 meters per second. There's no welds and standard parts. Our final mass is 750 kilograms. It has solar power utilization, and it can be disassembled and reassembled on site. Thermal regulation with conductive thermal regulation, and it can haul 750 kilogram payload 80 kilometers in 2.7 hours of continuous operations. So that's all I've got. This is obviously a starting point, but we're pretty excited about it. I hope you enjoyed the presentation and have a great day. I'm Laura Bahala from Kennesaw State University.